Okay, domain 2, good old security architecture and models. Okay, security architecture and models objectives. Basically, we're going to cover computer architecture, software and hardware components, operating system protection mechanisms, access control models, evaluation, assurance criterion and ratings, and then also certification and accreditation and attack types. As far as EC Council goes, there are actually 2 CNA certifications. How many people have heard of the CAP before? Which is Certification and Accreditation Professional. My understanding is that it was mainly pushed in regards to some contracts with the State Department. So it's mainly a CNA process for that side of the house. And then there's the ISSEP, which is a subsection of the CISSP, which basically means you have to pass your CISSP, then you can take your ISSAP. That actually used to be off of the DITSCAP model, but recently was changed to the DICAP model. Basically because a lot of people in the government sector are now using DICAP as opposed to DITSCAP. How many people here know what those terms mean? Basically it goes down to certification and accreditation or standards that the government uses for security baselines and so forth. There's a big argument that the DICAP is a little bit more or a little bit less, shall I say, instructive than the DITSCAP, but again, it's just the new standard. Okay, in this area, we're going to cover hardware and software, computer components, memory types and uses, storage types, process threads, and of course, language generations. And the higher the generation, again, the more potential for vulnerabilities because you're putting more code on top of other code. Okay, CPU, hardware components, central processing unit. Basically, this is a term that pretty much you have to memorize. CPU components, you're going to be looking at primary storage, your control unit, which is coordinates activities during program instructions and evaluation, then also arithmetic logic unit, or the ALU. Okay, CPU, processing data. In this area, instructions are data are passed for registers for processing. Basically, there's a control unit dictates when they can be processed by the ALU. Then also after execution, the results return to the requesting application's memory segment. And this is one of the issues or the biggest areas where buffer overflows happen. So what you end up doing is sending the shellcode or the opcode into the memory segment, and then the CPU processes it just like normal data. And then it sends it back to the memory address, and then what ends up happening with that aspect, if you do a NOP-SLED, which is the usually going to be an X90, or it's a no operations call for the CPU or the processor, it's going to slide right down into the actual opcode. And the whole point is try to get to the EIP area of the memory segment, which is going to be your return pointer, overwrite that, and now either A, at the worst case scenario, you've just destroyed the application and have done a denial of service on it because you now control the way that the application is running. And or the best case scenario is that you have your opcode or your shellcode in that memory segment. You point directly to that memory address or to the address that contains your NOP-SLED, which is going to slide you right into your shellcode, and now you just ran the exploit. And what a lot of people call shoveling a shell, which basically means from the system that you just exploited, you now have command interaction between that system, shovels the shell back to you, which is usually going to be, for example, like a bin shell on a Unix system or the CMD command prompt on a Windows box. So, but that's basically in this area. As far as the execution, where the data gets sent to the processor, it runs the data, not knowing if it's data or executable code. Okay, memory types. You have your primary memory. Memory directly addressable by the CPU are stored on an application's instruction and data. You have your real memory. It's memory segments that are available to the users. Your cache memory, which are buffers that increase the overall performance of the read activities. It also holds instructions that data can access. Also virtual memory, combination of real memory and secondary storage memory. Extends the available working memory of the operating system. For example, on Vista, they have the capability of if you put in a faster USB drive, it'll ask you if you want to use it as a memory or if you want to use it as a storage device. And in reality, that's probably the slowest memory you could ever use on a system, even though you can have the system lie to other software, because I know some software will not run if you do not have specific amounts of memory. So for example, if you're running a large application that says it's going to require 4 gig, but you only have 1, you can put in an 8 gig USB thumb drive, and it may be seen as, for example, like 9 gig for the OS, but you don't really have the 9 gig. What it's using that is for is a page file. So it's going to copy everything to one of the slowest ports on the system. It's going to go out the computer, go to the USB, transmit over the USB, store things on that disk, and then go back to the computer. So you're going to take a huge performance hit, but it still lies to the software and allows you to do other things that you probably couldn't do normally. But again, that's going to be your good old virtual memory. How many people have heard of the page file before on an operating system? Okay. For those who haven't, basically the page file is basically a file on the operating system that you dump data to, and it pretends to be memory. For example, pagefile.sys on Windows, a lot of things that are running currently there, if it doesn't need that information, it'll dump it to the page file and then run what's a priority or what's needed at that specific time. So there's a good possibility you may have usernames, passwords in a pagefile.sys. You could even have crypto keys, especially if the system is going through a crash. And on the forensic side, that's another reason why people really suggest for a Windows workstation to unplug the power immediately and then basically have everything dumped down, because if you turn it off, the garbage collection in Windows is supposed to empty out some of the content that's in the page file and would destroy the evidence. But on a Unix system or on a Mac, you are probably going to do more damage to the system by unplugging it rather than shutting it down normally. And then same thing with a Windows server, is that if you know that there's a server running on it, you're going to potentially do more damage to the database. So they suggest shutting it down gracefully as opposed to pulling the plug. Okay, virtual memory. You can have your frames in main memory. The application tries to use the main memory. When the memory is no longer needed, or if it needs more space, it goes to a swapping file, which then goes to the secondary storage. If it's the pagefile.sys, it would be located on the hard drive. On the Windows Vista example, it actually could be on a USB as well. So it hits that USB, then stores it. The fun thing about Vista, however, is they do encrypt it. So you can't use that and then basically go back as far as a forensic investigation and look at it through NCase or FTK and instantly see it. You'd actually have to decrypt it. Okay, memory management. Basically, responsibilities is keeping track of used and unused memory segments. Goes through, assigns memories segments to the processes, manages swapping between main memory and secondary storage, also has memory protection. How many people remember the good old blue screen of death, or the GPF? Basically, that was a scenario in most cases is where you have a program that's running in a specific memory area, and then somebody else goes outside the bounds of its protected space and either over encroaches on another application, and that's what crashes it, or the crash happens where it goes outside of its allocated memory space. But as far as the protection, there's only specific constraints to where the memory is supposed to go. And another thing is if you try to write to a protected memory for the operating system, that could also have a potential GPF or blue screen. And if I remember correctly, they changed the blue screen now to a black screen in Vista. So mainly marketing probably. Yeah. How many people have seen those commercials? The Mac versus PC? A couple of those marketing ones, like the bake sale, to where we're trying to raise money for the operating system because marketing took the rest of it. And then he said, just take a bite of the cupcake. Thanks for helping us out. $10 million. You have to pay me. You took a bite. So, yeah, definitely not to jab Microsoft too much about it, but it's one of those things to where it comes down to, that's just funny. Okay, also keeping track of software and virtual addressing. And multiple users, multi-user operating systems require more complex memory managers as well. Because in the scheme of things, you try to make it to where, again, the memory space is going to be protected, and you're not supposed to be able to jump out of your memory segment from user 1 to user 2 memory segment. I know with, how many people here have dealt with virtual machines before? I know there was an issue several years ago to where specific virtual machine company was being evaluated by an organization because they wanted to have different levels of information on a specific piece of hardware. And what was interesting about it was there was a flaw found within the VM environment that allowed the person to actually hijack some of the communication channels back and forth to the host, jump out of the VMware, go to the host, and then go back into another VMware session. So basically made it to where if you have different levels of security on the same hardware, at least for that VMware version and type, you were not able to use that product. But they've probably fixed it in future products. Those of you that do pen testing, antivirus can be your worst friend. It keeps your system safe, but then it can remove all your tools. So definitely be careful. With that being said, how many people here have played with the gold disk before? The gold disk? That's for if you're, basically if you work for government or contract or whatnot, you get the license to use pre-built scanning utility for their systems. You just can't do it commercially, but if your system connects to them, it's basically a way so they can do baselining, as they have specific patches that everybody should be at a minimum. And then it goes through, looks for registry settings, certain things for like cat 3 through 1, 3 being not as bad, 1 being you better fix it now. Yeah, you can break a system, and what's funny is there's John the Ripper, I believe, is still on there.
Yeah, it's still on there.
And a couple other tools will trip AV. So as soon as you put it in there, it's like, hey, I'm the security team. I should have rights to use this. But yeah, depending on how you run it, it can trip and flag you. Okay, accessing memory securely. You say controlling access to the system's memory. It's one of the most critical aspects of system security. Again, application hits the memory mapper. A memory hits a specific actual CPU stick or whatnot, or not CPU, but the RAM stick or DRAM. And again, it's supposed to make it to where it's protected and encapsulated. And then, of course, it's the CPU, comes back in, and then goes to the application. What's really interesting, though, how many people have heard about the memory swap issue with data? Basically, somebody goes in and they spray really a cold solution on memory stick, and they take it out of the system, and they can still get content off the memory or the DRAM stick. So as long as you freeze it, it basically freezes the registers in place, the ones and zeros or the electric portion. And I think other people are testing with Freon, which is not safe for the environment, by the way. Yeah, depending on what state you're in, you can actually get huge fines if you release it like that. But yeah, if you make it cold enough, you can get the stick to where all the memory that's currently in RAM, take it from that system, of course, keep it cold, then bring it into another system. Oh, thank you. And it looks like we have snacks. Well, that right there is lunch. That's what I've been having for lunch for the past week.
Yeah, exactly. We had all the carbs we needed. Along with the most spray of caffeine.
Oh yeah. Like I said, if anybody's interested in caffeine, Circuit City's right over there. And that 80-hour energy. Has anybody tried the 5-hour energy? They say there's no crash at the end. Well, you probably pass out if you drink too many, but that's basically the 5-hour energy, but just more concentrated. And on the 5-hour energy, you have two options. Drink it as the like 1 or 2 ounce shot, or however much is in that little really nasty container. It works great though. Or they suggest putting it into a larger drink, which is 16 ounces or so, so you don't taste it as much. Yeah, that stuff is a lot more concentrated than the other stuff, but it's the same content. Probably just distill a little bit more. And what's funny about it is they actually tell you to squirt it under your tongue, so it gets into your system a lot faster. Then there's also the stuff from Think Geek. Has anybody heard about like the Octane gel? That's basically a body gel that has caffeine in it, and they say put it on sensitive areas of your skin. Yeah. Yeah. So caffeine's definitely become an interesting drug recently. And then they also have shower gel. So if you don't want to put the body lotion on, definitely try shower gel and hand soap. And then of course what comes in the pack is not just the spray, but caffeinated gum. 2 pieces is the equivalent to 1 cup of coffee. Yeah, coffee tastes better, even if you don't like coffee. Oh yeah. And fortunately, you get to the point where Mountain Dew no longer affects you.
I knew some people that their doctors one lady was working in an emergency room and was living on Mountain Dew. She had like 8 or 9 a day.
Yeah.
And she almost had a heart attack. And her doctor tried to say,
Oh.
stop. Because the caffeine and sugar, they work.
Yeah.
Caffeine potentiates insulin.
Yeah.
So it's like you eat one donut with a cup of coffee, it's like to your body, it's like having 5 times the load of sugar.
Yeah.
Yeah, she almost died.
Ooh.
From Mountain Dew.
So I've known a couple of friends that one had a thyroid problem because of it. And so, yeah, it's definitely something that you might not want to do for the rest of your life because it would shorten the lifespan.
Yeah, just burn out.
But yeah, they call that burning the candle at both ends because you don't sleep for 72 hours at a time. Okay, hardware components, the buses. Basically, a data bus transfers instructions and data between components. Memory addressable bus is a data bus, basically like a highway. You have different pipes, you have different parallel lanes or whatnot. Memory bus is like the on-ramps to the highway. Basically, the more access ramps to the highway, the more addressable memory segments are on the system. Processes. This is an area that does tend to trick people up, such as, especially when it gets into threading, multi-threading versus multi-processing. Okay, process versus thread. A process is the application and users run as processes within the operating system. Process can contain several threads of code within inside of it, and threads are individual instruction sets. There's the different states. Of course, there's a stop state. Process is not running. There's the waiting state. Process is waiting for an interrupt to be able to process with the CPU. There's the running state. The process's instructions are being executed currently by the CPU. Then, of course, there's the ready state, which is available to be used and waiting for an instruction. And these are areas that, like a lot of the content in the CISSP, it's definitely good to memorize it because you may come across a question on that. But it's not a guarantee you will, but if you do, you may come across 1 or 2 questions. Okay, system functionality. There's multi-core, combines 2 or more independent cores into a single package composed of a single integrated circuit or IC called a die, and the more dies packaged together and so forth. There's multitasking, which operating system can process several programs at one time. There's the multiprocessing, it's basically a system with more than one CPU, and then there's the multiple programming, multiprogramming, which interweaves the execution of 2 or more programs in a CPU. So the core is basically when you have again the multiple cores and puts into one die in the system. So for example, like a lot of the computers, you'll hear the quad cores basically make it to where it's just higher computing power. And then the issue that a lot of people will come across, for example, is of course multiprocessing. So you have a system with 2 to 4 CPUs. If the operating system does not handle multiple processors, then basically you wasted the other processors. I know a lot of people that would, for example, how many people remember the 8-bit motherboards? There was a motherboard out there called the 8-bit BP6. It was really nice for overclockers. And people that do overclocking is they get a CPU and then they try to get it faster than what it was designed for, which is not a good business case to do because you've just shortened the lifespan of the item. But I remember getting one, and a lot of people that I was working with also got one. But you could actually put higher fans or heat sinks on it and get a 333. This was back in the day when those were relatively common, and overclock them up to 600 megahertz. So what ends up happening is you can easily get a little over a gig system before when the top was, I think it was the 500 megahertz systems. But they were dual processor. So if you ran Windows 98 on it, you're only going to be using the one processor at the 600 megahertz. But if you had, for example, some of the Linux OSs or some of the NT systems, then you'd be able to utilize both processors. And then, of course, the multiprocessing is the other issue, or is for the processors, but tasking is where multiple processes on the same system at the same time. Sometimes you'll come across where there's not true multitasking, to where it says that multiple programs can run at the same time, but it does what's basically called, goes through and prioritizes and says, okay, the CPU touches this, then it stops, then allows this one, then stops, and so forth. So it's kind of a virtualized multitasking. Okay, in this area, I'm going to cover self-system protection, or system self-protection. the levels of access to resources and trust levels. Of course, memory segmenting, process isolation, layered and data hiding, virtual machines, protection rings, security domains, and trusted computing base. In this area, you have your system modes. Of course, there's dedicated security mode. All users have a clearance and a need to know to access the information on the system. So with that being said, at that security level, they're all being trusted in that area. Does not require complex methods of controlling access between classification levels. And there's also probably not going to be caveats in there. Basically, an admin on that one system is going to have access to all data on that system. Okay, multi-level security mode. All users have a clearance to access the information on the system, but not a need to know. So there could be some sorts of caveats to where the individual has a need to know for specific content A through B, and then C through J, they do not have a need to know. So what ends up happening is they do not have access to it, even though they have the clearance level for that. You're going to see that a lot in higher level systems or like research and development companies, things like that, where they have R&D guys that are playing with a bunch of stuff that they don't want the development team to be able to play with. So again, it's going to be on the same system per se, but it's going to be segmented off. Okay, and then also 2 or more levels of classification can be used, and data is in compartments or caveats, which works as virtual containers. So again, you can be an admin of the entire network or at the top level, an administrator there, but the administrator only has rights to specific content, not the whole data system. You'll get that primarily, for example, the Orange Book. We're going to cover that a little bit later in access controls. The Orange Book covers the D1 security all the way through A1 security. So there's D1, which is basically no security. There's C1 and C2, which makes it to where it's like a Microsoft operating system has only been rated at C2, which means that there's usernames, passwords, there's different levels of user accounts, but you can't do any caveating. And then the B, which is the first layer of mandatory access control, which allows you to do, back down to the multi-layered security system, is that you can have several people at the same classification level, but the classification of the data itself has its own security label, where specific people at the same classification cannot get to the same data. Okay, levels of trust. Trusted processes have more privileges. Of course, processes of higher trust can access more system instructions to operate in privileged mode. And processes with lower trust can only access a smaller portion of system instructions and operate at the user mode. And what they try to do is separate the two, especially that's when it comes down to the rings of protection. The CPU architecture dictates the level of trust available to the system resources that can be accessed mainly through memory. And the CPU actually executes the instructions in different states depending upon the requests of the process's trust level, such as user mode versus privileged mode. And again, you have your good old protection schemes. The majority of the operating systems out there are going to be probably your 2-ring scheme. So you have your user and protected mode. The best case scenario, you of course have more layers to where you'd have, for example, like your system mode or your kernel level or kernel ring to where it does anything and everything. And then you have a layer where your operating system can communicate with that layer, which would then communicate with the kernel layer. And then the user layer, which would then communicate with the OS layer, which would communicate even further. So the more rings, the better. But with that being said, it's going to be more expensive to create each individual layer, each individual ring. For protection rings, separate the processes at different trust levels. The rings are provided by the CPU's architecture, and the operating system can be written to use some or all of the rings. The trusted computing base, or TCB. All mechanisms that provide protection for a system, such as software, firmware, the hardware, basically anything and everything within an environment. Basically a term originated from the Orange Book. The Orange Book is not required reading for the CISSP because the majority of the stuff, especially going to be in here, but it's basically a historical reference of how computer systems were supposed to be set up or how security was supposed to be designed within the system development lifecycle. For example, going back to the mandatory access control, the D through A level security ratings, things like that. Again, it's not going to be something that is common knowledge, which everybody knows in specific environments, but it's something that was created as a standard, and it is something that the majority of information security world, especially in the States, has been evolving to. Okay, the TCB is made up of trusted processes that are executed in the privileged mode, and security perimeters delineate what is within the TCB and the processes that are not within the trusted computing base. Okay, reference monitor. Of course, reference monitor, access control concepts refers to as an abstract machine. It also controls relationships between subjects and objects. Does anybody know the difference between a subject and an object? Because this type of wording will probably be, if not on this test, on other security-related tests.
Subject's a person, object's a file.
Yep. Or it could be subjects, even an application, databases can be the object. But yes, basically the subject interacts with the object. So when you're looking at the security levels, you need to take that in consideration, because if it's the user, you could have specific access controls specifically for that. Then you can even basically daisy chain them together to where the subject talks to the program talks to the database, and then so forth. So you can have layered security in that aspect as well. Okay, security kernel. In the trusted computing-based components that enforces the reference monitor's access rules, physical implementation of the reference monitor, and also security kernel is the portion of the TCB that is concerned specifically with access control. Is everybody comfortable with the term access control and the basic principles behind it? Basically, access control is determining what has access to a specific asset, which could be memory segment, could be data, could be a physical building. Okay, in this area, the models. This, again, is something you will have to memorize. These are terms that outside the CISSP you may come across, but are relatively rare, such as the state machine, the Bell-LaPadula, the Biba, Clark-Wilson, non-interference, and so forth. But the primary ones that especially you really need to know the difference of would be, for example, the difference between Bell-LaPadula and Biba. Bell-LaPadula is going to be more of your military mindset or your government mindset, to where you have the classification levels, and you do not want higher information being written to a lower classification level. Lower can be written up, but higher cannot be written down, because you don't want the guys seeing it. The other one, Biba, is basically the reverse, because it makes it to where they want integrity of the data to be there. So as far as they don't want people at a higher classification level being able to read potentially bad data from a lower classification level. But as far as a higher, they might be able to write to it because that's more trusted. Okay, access control models. Okay, the models, these provide rules and structures to be used to control the access and shows how access decisions are being made. The main components, again, are going to be your subjects, your objects, your operations, and of course their relationships. Then the goal is to control how objects are accessed, basically to ensure one security principle or another, such as confidentiality, integrity. Availability is not really part of any of the models. For the main reason is that that's more of an IT issue as far as business continuity planning. But everybody comfortable with the difference between confidentiality and integrity? For example, encryption can provide for both. For the main reason is whenever you put a plain text in a ciphertext, if it gets changed, then basically the confidentiality has been tampered with. The person may or may not have been able to read it. They'd have to crack the encryption key or whatnot. But you're also able to tell with the integrity of the message, because the encryption portion changed. So you can validate both the confidentiality and integrity. But if you do digital signatures, that's not going to be confidentiality, because you're just making a hash basically, or a digital signature to the message. And what they end up seeing through the email, for example, is that the hash matches, therefore it hasn't been altered during transit. So that does the integrity of the message, while encryption can actually do both. Because some encryption will actually put digital signatures on it as well, which is kind of a double whammy. Okay, access control models, the state machine. Model characteristics deals with the system state transitions as activities take place within the system. It's also for each possible initial state, there is an execution sequence for each possible state transformation. There must be mappings for each state change, abstract in nature, and does not specify protection mechanisms or meanings of enforcement model. And if a system comes up in secure state and shuts down in secure state, the system is secure. And usually what they want is if it comes up in the secure state, if it crashes, it should also be in a secure state. Okay, information flow. This model, information must flow securely through the state machine system. Basically, input introduced a state machine transaction, and specific outputs would be pushed through. 4 possible information flows. There's your input to output, input to next system state, state to state, and of course your state to output. Then whatever component directly affects the flow of information must dominate all the components involved within the flow of the information. Okay, Bell Lapadula. Hopefully I'm pronouncing it correctly. But basically it comes down to it's a confidentiality model. So this is the easiest way to remember it because you will probably be pushed on it. Because again, with the history of the ISC² organization, a lot of them are ex-government or ex-military. So that's another reason why they really push the Orange Book. But this right here, confidentiality, Bell Lapadula is going to be your military model. Information flow model where information cannot flow to an object of lesser or non-comparable classification. So for example, if you're on a sensitive network and you're trying to get stuff to an FOUO network or an unclassified network, it's not supposed to flow downhill. But information can flow uphill. So you can read the stuff at the lower classification. But the trick too is if you have, for example, unclassified on a confidential network, then technically you have to go through the paperwork to put that unclassified back onto the confidential because you don't know if it's been changed, altered, or if it actually holds higher classification of data. So again, it's going to be your one-way flow. If there are scenarios to where individuals will have one-way guards. Has anybody heard of that before? One-way guards, usually a hardware piece which makes it to where traffic will go one direction and not the other. Basically allows you to have your classified networks such as trade secret information from your research and development network, and have it to where you can get log files off a lower classification and read the log files. I know a lot of organizations will have it to where say IDS logs or security logs, security scans. They don't want them at the same classification of the system that they're scanning, so they usually upgrade the classification. For example, if it's on an unclassified network, they'll at least put it on an FOUO. If it's FOUO, it might go to secret or top secret or whatnot. But basically, a lot of organizations see that as information that could potentially be damaging to the network that it's on, so they upgrade it. And the only way you can do that is to have one-way guards. So it's a mathematical model that uses a set of theory to define access rights while keeping a secure operating system state. So you have any activity will always result in a secure state. Maps a subject's security clearance to an object's classification and creates a dominance relationship. So when it comes down to it, again, if the person is trusted at a confidential level, then they'll be able to see anything at confidential or lower. With the caveats being, going back to the mandatory access control model, is that even though they may still have the good old clearance capability, they may not have a need to know. So then it comes down to the third variable for the caveat. Okay, the clearance of the subject again, attempting to access the object is compared with that object's classification. So again, they cannot get higher classification level. And the rule is subjects cannot read data from an object at a higher level, and subjects cannot write to an object of a lower security classification or security label. So again, it's keeping everything at the specific content. And the majority of systems that you'll probably see at this level may not be protected just by software, but may also be protected at a hardware layer, usually are. Subjects must only read-write at their own level. Again, you will see scenarios to where on a confidential network, they're going to have their proprietary information, and then they may have unclassified or unsensitive information on that same network. For the main reason is to minimize the need for access to multiple environments. For example, you may have an environment that has nothing but confidential information on it, and then you may have a single access point to get onto the internet, which is going to have your public information on it. So you'd still be able to do your research, your information gathering, basically anything you need to do on that one system, but it's not physically touching any of the other systems. Okay, but yeah, definitely memorize that Bell LaPadula is the good old military type. Biba, the opposite. So when it comes down to it, it's the integrity model. No subject can depend on an object of lesser integrity. So basically, they don't want you reading anything at a lower classification level because it may taint the information that you have at a higher classification level. Based on a hierarchical of a lattice of integrity levels, authorized users must perform correct and safe procedures. The two main things to memorize for it is going to be there's going to be no write up and no read down, as opposed to the opposite, no write down and no read up. So Biba is going to be your commercial mindset as far as integrity. You don't care about the confidentiality of the data. You're looking more for the integrity of the data.
What do you mean by, like, you can't, so the higher ups cannot read lower?
Right. It makes it
Because
to where,
it might taint,
yeah.
okay.
Because if they were trusted enough to be at the higher level, they would be at the higher level. So any information at that layer is suspect. So it could even be at the aspect where you're assuming that everything's been compromised. So from that aspect, you can have it to where anybody in the DMZ, you're not trusting any data coming from that system. So Clark-Wilson is also in an integrity model. Model for commercial integrity, instead of addressing disclosure, requires well-formed transactions and separation of duties. Again, does everybody understand the concept of separation of duties? Probably cover it half a dozen more times next week. But that's another huge thing that's probably going to be pushed, at least the mindset-wise on the CISSP, is that if you have multiple people doing the same job, that's one thing. But if you have one person doing multiple jobs, then there's more potential for security issues, such as collusion, which means two people working together to steal things and so forth, or data leakage. Okay, well, Biba and Bell LaPadula use a lattice approach. This model partitions objects into programs and data. Access equals triple, such as a subject must go through a program to access and modify data with an object. So the subject may be at a specific classification level, but they do not have direct access to the object. They have to have access to the program, which may or may not have access to the data. Okay, again, separation of duties, access through programs, and of course auditing. So the things, again, to memorize is Bell LaPadula is confidentiality, Biba is integrity, and Clark-Wilson is also an integrity model. Okay, non-interference. This is developed by those two guys. Not even going to try to butcher their name. It's based on a set of theory where the users are separated into different domains. An output stream remains unchanged when the input comes from levels that are less dominant. And a subject cannot be influenced by behavior of other subjects at a higher security level. Okay, lattice-based. Again, so I mentioned before, Biba and Bell LaPadula are going to be lattice-based controls. Every pair of elements has partially ordered set of greater and lower bound, basically least privilege type areas. For example, again, if you are going to be at PII level, it's going to be to where you have to stick at that level either higher to that level or lower to that level. For example, back in Biba, you can read anything higher than you, but not lower than that baseline. And then the Bell LaPadula, you can read everything up to that baseline, just nothing higher than that. Form of MAC, which is mandatory access control, where security classes are set up and control how the subjects are accessing the objects. Again, security classes, top secret, secret, public, PII, basically just the security level of the individual. Then also there's the classification label of the actual object. Rules are set to dictate how the information can flow from one class to the other, such as the up, the down, so forth. And confidential information can flow to an object or subject that is working in the class of secret. For example, confidentiality can go up to secret on that network. Secret can go up to TS, but if it's Biba, then it would be basically the vice versa. Okay, access control matrix model. This is a two-dimensional matrix representative of subjects in rows and objects as columns. Again, specifies the operating or operations and access rights allowed for each subject as it relates to the specific objects. Again, it has ACLs. Everybody comfortable with ACL is again? The access control list. Basically, it's kind of a database that says you can or cannot do specific items. You'll come across this a lot, especially if you have a networking background with like firewalls and routers. So, okay, capabilities. Protected identifier that recognizes the object and access rights allowed for the subject, and it is bound to the subject. Okay, model characteristics. Again, this is the Chinese wall model, published in '89 to ensure fair competition. Mathematical theory used to implement dynamically changing access permissions. Defines a wall and develops a set of rules that ensure that no subject accesses objects on the other side of the wall. Individuals are only allowed to access data that does not present conflicts of interest. And also weighs the system competitors, or separating competitors' data within the same integrated database. Would be a good example of that. Any type of database that would have different entities in it, or a system that would have different entities on it. For example, hosted applications. You may have a website that has, say, 500 domains on it. Several of them may be different service providers or web design companies or whatnot. That's a scenario to where not just in a database, because you may actually use the same backend database, but that data would have to be separated, not only the information in the database, but the information on the page in the subfolders and such from each other. So one system can't go into their folder, and then do directory transversal to go back into the competitor's system. So you basically try to sandbox everybody in that specific classification level into only what they're allowed to see. It also tries to ensure that the users do not make fraudulent modifications to objects. Again, if you do or are able to get to your competitor's data, to be able to basically state that the price of a specific application that they're selling, instead of $1,000, is now $1. So now if they have 500 people purchase it, they may now be in a deficit. How many people here have heard of e-shoplifting? It's a variable manipulation attack, going back to changing parameters and such. Basically has it to where you're no longer checking, or you have not been checking the data on the server side, you're only checking it on the client side. So for example, you have price, you put that on a web page, and then the server does not validate the part number and the actual price in the database with the part number. And there are a lot of websites out there that are vulnerable to this, mainly because they don't want a database. So what ends up happening is you intercept the traffic from the web page up to the server, change the price, and from the server, it's concerned with what information went to it. So therefore, instead of $1,000, you push $1 up to it. Now you can purchase the item for $1 from the server. There actually has been a court case where an individual got in trouble for that, bought some stuff online on a store. They actually shipped it to the individual, and they found out the mistake whenever they were doing auditing. And they went back to the individual, say, you only paid, I think it was about 99 cents. You owe us this much more money, which was, I believe, over $1,000. And the guy said, nope, not paying you. So I went to court. The guy actually won the court case because when it came down to it, was his defense was bartering. Is that the server, the website, said it was one price. He said, no, I'm not going to pay that price. He sent a counter offer back to the server. The server then accepted, and therefore the transaction was complete. So I wouldn't suggest doing that, because depending on jurisdiction and how good your lawyer is and how good the other lawyer is, that may not fly. But I would never do something like that unless it's a pen test. And you always want to look for those holes. There's also the Brewer and Nash model. Basically data representing each company. Organization A has their data. Organization B has their data. Of course, they try to separate or sandbox each individual environment so one can't jump from one to the other. Take and grant model. Basic model characteristics. It's a mathematical framework used for granting and revoking access authorization. Also, analytical tool for auditors to test software security, and rules for how users users transfer their permissions to other users. For example, if you are a power user, if you created another user, they should not be able to take any rights that you do not have. They should only take at maximum what you are allowed to give them. And the same thing, if somebody tries to get rights from another user, you should only be able to get the rights that that specific user has. Whenever, for example, you're cloning user from one to the other, it's you can't go above and beyond the scope of the resource that you're trying to get from. Yes?
Are there any, with respect to the various models, are there any products out there that allow you to implement that framework, or is it
No.
more of a guideline?
It's a guideline. For example, there's a lot of entities that are required to be mandatory access control, but they have Windows boxes, and Windows cannot go to a B level for mandatory access control. It's just not physically possible for the operating system to do because of the way it was architectured. So in that aspect, then you have to keep that model in place, you now have to segment out the network physically so one network doesn't talk to the other network. Either that or get rid of all the Microsoft operating systems on that network and replace them with like secure Linux or Solaris or whatever other Unix allows for mandatory access control. So
How do you evaluate which model would be most appropriate for
the environment, for example, with the military or government type sector, to where you have information that could be national security interests. You are not wanting anybody to get sensitive information above what they should have. So you will, by default, use that model, which doesn't necessarily mean the operating system or the software you will, but the entire environment is going to emulate that model. And unfortunately, nothing is perfect. For example, like the Orange Book, they went through the D through A. There's only one system that I know of that actually spent the money to become A1 certified, which is basically the same thing as B3, which means it has the mandatory access control, it prevents covert channels, it does anything and everything to make sure the whole environment is secure. But the difference is from B3 to A1 is that basically everything's documented and proven. So during the whole design, they have certain security things saying nothing's been altered during the design, the implementation, and even in shipping, they may have it to where they have armed guards transporting the device from one area to the other until it's actually in production. And I believe that was Honeywell. But it was so expensive, it was cost prohibitive to actually get that high. And you'll see that a lot with the majority of the models. For example, like the CMM levels, a lot of people will not go all the way up to 5 because it's relatively easy and cheap to go from level 1 or 0 to 1. And then it's more expensive, basically exponentially, to go from 2 to 3 and then all the way up to 4. But if you get up to 4, you're going to do your basic 80-20 rule, is the majority of the vulnerabilities are going to be accounted for. So if anything does bad happen, it's, in all honesty, it's probably going to go down to the prudent man principle or prudent person principle, to where you're doing what everybody else is doing. But a lot of people go to the 5 is because they have specific industry segment issues, or they have marketing things that they want to get contracts for. So that's why they don't go all the way up to the 5. But for an example, going from 0 to 4 might be just as expensive as going from 4 to 5. Just the cost level sometimes just isn't worth it. So no, it's just basically a whole framework that they want you to try to go through, and whatever it takes you to get there. And as far as the way it was originally designed, it was, you wanted the OS to do it yourself, so you can caveat specific systems within the OS. But then realistically, as far as the cost of products, inherently Windows 2000 server is going to be cheaper than a big mainframe server type scenario. So, but no. Okay, security evaluations. You look at the Trusted Computer System Evaluation Criteria, the TCSEC. These are numbers and names that you basically have to memorize. So there's the ITSEC, which is Information Technology Security Evaluation Criteria, and the good old common criteria. Okay, you have your TCSEC. TCSEC characteristics, developed by the National Computer Security Center. Basically, it is the Orange Book, based on the Bell-LaPadula model. And again, what does Bell-LaPadula look for? Confidentiality. So what are the axioms for the confidentiality? As far as read-write, what direction does it go? Yep, no read up, no write down. What about the Biba? Yeah. Other way around. So, yeah, no read down and then no write up. And the reason why I definitely push this, because each domain is going to have a certain percentage of questions. And this domain, honestly, is not nearly as big as, let's say, the telecommunications domain. So there's specific things you basically just need to memorize. And I'm going to come back to here, but going back to the beginning. For example, all of these access controls, you need to memorize.
I have a question on the Biba. Can you, so you say like a financial institution would be most likely to use that model.
Yeah.
Can you break that down to just somebody at Bank of America, a practical example of why a higher up
DMZ.
What's that?
DMZ, for example. Let's say if you have your website database on the DMZ, and then you have your real database on the inside,
Right.
you wouldn't want to trust the data on here, which is potentially suspect because it has more exposure
Right.
than you would the system that is supposedly protected
Right.
by either multiple firewalls or a completely different network segment. So that's the main reason from a financial aspect that you'd want it, is because you have to assume that lower side has been compromised. Same thing with the Bell Lapidula, is you have to assume that the lower has been compromised, and you just don't want the bad guys having the sensitive information versus the Biba. You don't want bad content being injected into your production data. So again, there are ways that in real life, a lot of people are trying to mesh the two, as far as they don't want specific people reading content from a higher classification. They also don't want them altering it. So a lot of times they'll segment the networks altogether. So it's basically a combination of both. But from the Biba, that's the primary aspect, is you don't want bad input being influencing.
Stable environment,
Yeah. Yeah, for example, how many people here have dealt or have seen SQL injection before? So basically when you send malicious content through, for example, like a form script, it hits the web server and then potentially goes into a database. If you do not segment your network off, if that database is then used by internal resources, or it is your internal database for the rest of your organization, if somebody's able to do SQL injection, they may be able to drop tables, alter data. If they're able to alter data, they may be able to find out, for example, account numbers or account names, and then move it from one account to the other in a financial institution. So that's one of the primary reasons. But again, in this area, memorize all the models. And the primary ones are, of course, going to be your Bell Lapidula, and then your Biba, and then Clark Wilson. Okay, TCSEC. Alias the Orange Book has 6 fundamental requirements. Of course, there's the security policy. This is well-defined policy enforced by the product. There's the marking or labels associated with the object, which goes back down to the classification portion. Again, if you have a clearance level of FOUO, but the object itself is labeled as confidential, you wouldn't be able to access it. There's the accountability, audit data collected and protected, identification, individuals, identification of the subjects, again, which basically says, okay, you are the individual, you do have classification right of FOUO or SBU, and continuous protection. So this is basically where trusted mechanisms that enforce the policy must always be protected against unauthorized changes or tampering. How many people here have dealt with change control? That's a fun process. In the perfect world, it works to where if there's a change that needs to be in the environment, it gets submitted to a change control review board. They look at it and say that, yes, we'll put this in there because it doesn't harm the security posture of the organization. It improves it or fixes whatever you want it to deal with. So yeah, in the perfect world, it's relatively quick. It only goes through maybe a couple bounces or whatnot and prevents people from inserting bad input, basically installing things they shouldn't install. For example, I know some places do not like Winamp. because it's unauthorized. They don't like that commercial applications. They're trying to minimize other outside pieces of software. Picking on WinApp specifically because there's a couple of vulnerabilities with it within the last year or so, to where if there was a malformed, M3U, the PLS file, and then their other file extension that they read for streaming media, you could actually do a local exploit. So it loads the content locally and then runs the exploit, and then you can take over the system. A lot of people have what's called basically trusted software. So they have their database of software that they've tested, they've authorized on their network, and then if you add anything else, you have to go through the change review process. Unfortunately, I've seen a lot of scenarios to where they will go through this entire time-intensive process, and it unfortunately breaks in real life sometimes if too much politics gets put into it. But a lot of people do not consider scripts or scripting languages as something that should have to go through a change control board or change review process. Scripts are basically just as powerful as an executable, except they're more so because then you can change them on the fly if you want, then just rerun it. I've seen many scenarios where I personally like it because sometimes helps you out, but from a security posture, it's the worst thing that could happen, is the good old moniker of it's easier to ask for forgiveness than it is for permission. So a lot of people write scripts, run things, and then either try to fix something or try to improve upon a current process. But if nothing bad happens, a lot of people just say it's okay. But as soon as something hits the fan, then of course it goes back to a break in the change and review process. But this right here, as far as the continuous protection, they really push like change control and review boards. Then also the assurance mechanisms evaluated separately to ensure that the system enforces the security policy, and for multiple reasons. A, things break over time. Also, things change over time. So something that worked 20 years ago may not necessarily work now, especially with the change of attacks and change of technology. I know a lot of software pieces. For example, you write a Windows app. If you wrote it for NT4, communicating with the Win API, the same calls are probably not going to work with 2003 server, or not all the same calls, because some of them change over time. Some of the access rights are different. I know some of the pieces of software will run as different accounts. For example, IIS5, that ran as a system account. So if you did a buffer overflow on IIS5, back for example like 2000 server, unpatched, you could do that, and there's a couple buffer overflows that will give you system access. But in future IIS like 6, they have it to where it's no longer running as a system account. So if you buffer overflow it, it's going to have different access than your basic system. And system's the worst access that you can ever grant somebody, because now they have full 100% access on the system. SID 500, which is the local system administrator, that only has about 95% access to the system, because there's a few registry files, a few pieces of data that they can't get to because it's locked by the operating system. So again, with the assurance testing, that's a big issue, is that things change over time. People upgrade, or even people change as well, which can make it to where the security baseline is no longer valid. So that's another reason why you always have to test. Okay, these, again, something for memorization. Study time for tonight. Okay, you have your A1. This is verified protection. Formal methods. And basically when it comes down to it, the only difference between A1 and B3 is the verification, such as like the CMM process from 4 to 5. It goes from managed to optimized, is that there's just more paperwork or more processes that you have to go through to ensure nothing's changed along the way. There's B1, B2, B3. That's mandatory access control. If you do run Linux, the NSA basically rewrote part of the kernel or the Red Hat kernel and then made secure Linux or SEC Linux, and this was probably this was many years ago. I guess not many, but a few years ago. But a lot of the distributions have that by default now. So if you're installing it, it will install that unless you actually turn it off, and then it won't. But makes it to where Linux boxes can now do mandatory access control. There's the C1 and C2 for discretionary protection, and then of course D for minimal. Again, you will need to know the difference. A1 is going to be the top of the line, and then B, even though it's kind of going backwards because A through C or through D, D is the least, but the highest number is going to be the highest protection. The soonest letter is going to be the highest protection. So of course, B3 is more secure than B1, but B1 is more secure than C2.
That makes sense if they're a good developer.
Yeah.
DoD.
Yeah.
Yeah, it's not, if you think of it like it's like an upgraded version, I guess. Like B3 is the upgraded version of B1.
Yeah. So yeah, they assume that everything's perfect, and then it just goes downhill from there.
If you have a Windows box that runs only one classification, that's fine, right?
Yeah.
You were saying just a minute ago, Windows can't.
Yeah, Windows
you
has not
can't
been
do
certified
that.
higher than C2.
Okay,
So on a technicality, if you just have a Windows network
right.
with multiple classifications on it, you cannot do mandatory access control. You would have to have potentially other sort of software, such as like a VM type environment running on top of Windows. But then even with that, you would have to, yeah. So yeah, depending on the vendor or whatnot. But see, that's the interesting thing about like B3. It prevents covert channels from happening. And basically a covert channel is using a communications method for something other than it was initially designed for, which could be as advanced as jumping into memory and then finding out what another program is writing to the stacks or whatnot, then copying that back out and then putting it into your app. It could be, I know an individual that recently spoke at the Red Team Blue Team Symposium and was talking about IPv6 communications channels, or covert communications channel, to where he stuck data inside of the IPv6 packet and then sent it to a system or to a network. And then once it hit the network, it was looking for the administrative packets, what was in there, and he was able to communicate with up to 5 different windows at once. So it could be on 5 different systems, or it could be one system with a lot more data. And what was cool about it was he released this, I believe it was either Black Hat or DEF CON a couple years ago. And the funny part was he set up his little IPv4 network, and everybody said, well, that's just tunneling IPv4 over IPv6. He goes, no, you're not listening. Look at what's going on. And he was doing the IPv6 over IPv4 as a basic tunneling mechanism so he could get it out of his network, bounce it to a country, I believe it was Sweden or the UK, then bounce it back into the States, and then bounce it back to him. So he was basically going an international path through IPv4 because that's the internet regular protocol, but then his system was decapsulating it, putting it in IPv6, and then ripping apart the IPv6 packet, which had all the real data inside of it. So that's a more advanced communications or covert channel, but then you get some of the basic ones to where people be running SSH over port 443 because it's running an SSL type encryption, but it's not HTTPS encryption, it's SSH encryption. So, but as far as the covert channels, MS is just, or Microsoft OS is just not designed for it at this time because they want more usability rather than security, in all honesty. Is because if they wrote their OS like a Unix box, they'd probably, some of the users would drop off like flies. The mom and pop shops would be calling in for tech support because they wouldn't be able to get specific applications to run. And that's also one of the biggest reasons why they're a huge target, is because, for example, on Windows and Linux systems, people that use those as workstations, I hate to say it, but they're usually at a higher technical level than somebody running a Windows system. For the main reason, because a lot of the utilities are command line, and people that are point and click hate command line. So they don't want to have to configure a conf file for their ETH0 or their Wi-Fi card. They just want to be able to run a utility, have it up and run. Linux has been getting a little bit better graphically for that, but it's still not nowhere near where Windows is with that aspect. So the whole market share is different too. But yeah, you can do security at the B level if you segment the network at the hardware level. Okay, full Rainbow series was developed, it's 26 books in all, covering items not addressed in the Orange Book. And the Red Book is the Trusted Network Interpretation, or the TNI. So you need to know the difference between the Orange Book and the Red Book. And you need to know that the Orange Book is AKA the TCSEC, which goes back to Trusted Computer System Evaluation Criteria.
The orange book is, I'm sorry?
The Orange Book is TCSEC, or TCSEC is the Orange Book. They're one and the same. And I hate to say it, in the perfect world, this works great. It's just when you take in budgeting and real environments and user capabilities, it makes it to where it's not feasible to have an A1 system just because of the cost of the verification. Okay, good old ITSEC. This is Information Technology Security Evaluation Criteria. It was created in '91 by our friends across the pond, European nations, including Germany, France, Netherlands, and the UK. Evaluates functionality and assurance. Basically, the difference is, of course, may not be able to function properly on the ITSEC, but if it's secure, it's good to go. With them, they basically took that into account as well as the functionality of actually doing what it's originally designed to do. Evaluates functionality and assurance separately. And again, it's going to go to the lowest common denominator. Because you can have, for example, a rating of E6 for assurance, but functionality is only an F2, then technically you're only going to go to what's held within the F2 rating. And basically the correctness and effectiveness pertain to the development of the product. So for example, with F2, even though you may have an A6, which would be the equivalent to an A1, it's still only going to be at your quote-unquote C2 level because the functionality is just not there. So I guess on a technicality, if you have a brick, if it's the rock brick is guarded by an 18-year-old with an M16, it's extremely secure, but it doesn't do anything, so therefore it probably wouldn't pass too high, at least in the ITSEC. The TSEC would be A1, as long as it's documented, though. Okay, you will come across probably the E and F ratings, but the things definitely to memorize are going to be the TSEC ratings. Again, with the background of the ISC squared, where its origins were, there were a lot of people within the, or ex-military that were in that organization.
So we need to know how they, the IT-SEC and the TSEC ratings relate to each other previously. We need to know that.
It's good to know. Chances are you will not get that many questions. Back to the contract, you should not get questions. Not you shall, because there's always the possibility. But I have seen people historically get the good old TSEC. So definitely know the difference between the D1 through A1. The F1, E1 combo, it's going to be the same as the C1. The primary things you definitely need to memorize, especially the TSEC, and it's good to know the ITSEC as far as that it has an E through F. And it goes all the way up to F10. However, the majority of the stuff in this area is going to be far beyond what is logistically feasible for most organizations. Okay, ITSEC, good and bad. The advantages, basically assessing the functionality and assurance provides more granularity of the product, and also deals with the items above and beyond the good old Orange Book. Disadvantages, increases the amount of rating combinations, because again, you can have an E6 security rating, but if the functionality is that of basically a brick, you may only have an F1, which means that you're going back in the equivalent to a C1. Okay, still do not provide all the answers for the evaluation process. Common criteria. This is something that, again, basically just need to memorize. The EALs are basically parts of the common criteria. This is an international standard. The International Organization of Standards, the ISO, created this evaluation in 1993. The TSEC was too rigid for a lot of organizations. It did not take many things into account. The ITSEC provides more flexibility, but added more complexity with its attempts. And so basically they made the CC with the TSEC, the ITSEC, the Canadian Trust Computer Product Evaluation Criteria, and the federal criteria. So they combined everything into one big happy family standard. Okay, the CC components. You have your protection profile, description of needed security solutions. There's, of course, the real-world need. There's the target of evaluation, which is product proposed to provide needed security solutions. Security target. This is written by the vendor explaining security functionality and assurance. And, of course, there's the packages, which are the evaluation assurance levels. So you need to know the difference between the CC and the EALs. The CC is the standard, or the common criteria evaluation area, and the EAL basically the grades within the CC. This basically describes what must be met to achieve effective EL ratings.